Okay, so starting with 22, true or false, a function f is decreasing and is concave up, then the rate of change of f is negative and is getting larger when moving from left to right along the graph. Explain. So we kind of draw what this might look like. Can make it something kind of like this. So this is concave up, and our slope is negative. So if we look here though, our slope starts off with something kind of like this here, but it ends off much flatter here. So remember, concave up, you get something kind of shaped like this. So the question is asking, is the rate of change is negative, which is true, and it is getting larger when moving from left to right. So we're going from here to here, and our rate of change is getting larger. Well, that's kind of the definition of concave up, is that our slope is going to be increasing as we move along. So even though we're decreasing here, our slope is getting larger, or at the very least, even though it's negative, it's still getting larger as it goes. So this one here is true, because again, the definition of concave up is that the slope is getting larger, and if our function is decreasing, then the rate of change is negative. So both those parts here, negative and getting larger, is true. Okay, so we're looking at 23a. So we have a function f with the average rate of change shown in the table. Would you expect the graph of f to be increasing, decreasing, or neither on the interval from -2 to 6? So here to here, so the whole thing that we're given. So we would expect it to be decreasing on this interval, because if we look, all of our average rates of change are negative. If we have a negative rate of change, that means we have a negative slope, or we're decreasing, okay? And for part B, would you expect the graph of f to be concave up, concave down, or neither on the interval from -2 to 6, and explain? So this one, we would expect it to be concave up, because if we look, we start with our average rate of change being -1.5, and we end with it being -0.02. So what's happening is our average rate of change is increasing, or you might say it's becoming less negative, but either way, it's increasing. So if your average rate of change is increasing, what that means is that you are concave up. Okay, so moving on to 24 here, find the limit as x approaches infinity for each of the following, and explain your thinking without the use of a graphing calculator. So starting with A, we have 1,000 over x plus 1. So if x goes to infinity, we're going to get some really big number in our denominator. So because our denominator is so much bigger than our numerator, what we get is that y is going to go towards 0. Oops, 0. And if we look at part B, we have 5 minus 1 over x as x goes to infinity. So 1 over x as x goes to infinity, well, 1 over, say, a really big number like 10 billion is basically 0. So we're going to have 5 minus 0. So this one we can expect to be 5, okay? And for this one, for part C, y equals x minus 4 over x squared plus 1. Okay, there's kind of two ways to approach this. The first is to just, we can see that we have a bigger order in the denominator because of this x squared, which means that our denominator is going to get bigger much faster than our numerator, so we should expect it to be 0. But there's kind of a cool way that we can work through this more algebraically to demonstrate that. So really quickly, y equals x minus 4 over x squared plus 1. So what we can do is take each term and divide it by kind of our highest power. So we're going to take this, we're going to multiply it by 1 over x squared over 1 over x squared. So we're just basically multiplying by 1, but we're rewriting everything. So if we do this, we get y equals 1 over x minus 4 over x squared divided by 1 plus 1 over x squared. So if we look at these, as x becomes really big, 1 over x is 0. minus 4 over x becomes 0 as well, over 1 plus basically 0 again. So all of this, we get 0 minus 0 over 1 plus 0, or we could just say y equals 0. Okay, so on number 25, we are taking the limit as x goes to infinity of y equals x minus a over x minus b, where a and b are real numbers, and explain your thinking without a calculator. So just by looking at this, we can kind of see that a and b are just numbers, while x is going towards infinity. And whenever we have two x's that have the same power in the numerator and denominator, usually we can expect the answer is just going to be the coefficients divided. That's kind of like a shortcut, is we can expect it'll be 1 over 1. But to show this kind of more as a written out answer, we have y equals x minus a over x minus b. And just like on the last answer, we can take this and multiply it by 1 over whatever our highest power is. So in this case, we just have x. We're just going to multiply by 1 over x and 1 over x. So if we do this, we get y equals 1 minus a over x divided by 1 minus b over x. So if we take the limit of this as x goes to infinity, a over x is just going to be 0, right? Because a is just some number. It's not going to be growing, just like how x would be going towards infinity. And the same thing goes for b. So whenever we apply our limit, this is just going to be 1 minus 0 over 1 minus 0. So our answer is just going to be 1. Oops. Okay, so starting with 26a, salt water is flowing into a large tank, and the concentration C of salt is given by this function in pounds per gallon, where T is time in minutes after salt water started flowing into the tank. What is the concentration of salt water 10 minutes after the salt started flowing? So all that we're asked for is f of 10, which is just going to be 1.2 times 10 over 100 plus 6 times 10. So if we go ahead and work this out, we get 12 over 160, or just we can write f of 10 equals 0.075, and we need to include units, pounds per gallon. Okay, and for 26b, what happens to the salt concentration in the tank as T approaches infinity? So what we can do here is we can take the limit as T goes to infinity, and if we look here, we have T to the first power here in the numerator and the denominator as sort of our highest degree. So what we do is we're going to take 1.2 T over 100 plus 6T, and we're going to multiply this by 1 over T divided by 1 over T. So if we do this, we get 1.2 divided by 100 over T plus 6. So now if we just take the limit as T approaches infinity, we're going to have 1.2 over 100 divided by a really big number plus 6, or basically just 1.2 divided by 0 plus 6. So we can expect that the salt concentration as we go towards an T equals infinity, or we just let it be for forever, is going to be 1.2 divided by 6, which is the same thing as 0.2. So we can go ahead and write 0.2, and we need to include units again, so pounds per gallon. Okay, so for 27a, we're going to fill in the blank with the following limits. So we have, if f of x equals 6 minus 5x, then as x approaches infinity, f of x equals what? So real quick, 6 minus 5x might look something like that. So we can see as x approaches infinity, this is just going to go off to negative infinity. Oops. Okay. And then for part B here, if g of x equals 3 as x approaches infinity, and h of x is 7 times g of x minus 2, then as x approaches infinity, h of x will equal... Okay, so the two things that we can kind of look at is this 7 and this negative 2. The 7 and the negative 2 don't really care what x is, because no matter what, it's just going to be 7 times whatever g of x is, and then minus 2. So really, we can kind of think about this as 7 times the limit as x approaches infinity of g of x minus 2. And we know this portion here, the limit as x approaches infinity of g of x is just going to be 3. So really all we have is 7 times 3 minus 2, which is just going to be 19. And again, that's because this 7 and this minus 2 don't really have an x necessarily attached to them. The 7 kind of does because it has this g of x, but we're told that the limit of that is going to approach 3. So we just get to kind of plug that in directly and solve. So this one here should be 19. All right, so for number 28, we have a rock getting tossed into a pond, creating a circular ripple with area A equals f of r in square meters when it has a radius r meters. The radius is given by a function r equals h of t meters for any t time in seconds after the rock hits the water. What is the meaning of f of h of t? So if we look here, really our input is that t in seconds, and our final output is f, which is the area of the ripple. So whenever we combine these two functions together, the meaning is basically a function of the area for a given time t. Okay, so moving on to 29, let f of x equal g of h of x. For each part listed below, find two sets of possible formulas for h of x and for g of x. And g of x cannot equal just x, and same for h of x. So these questions can be a little bit tricky, and sometimes you just have to kind of think about them a little bit. But generally, you want to look for sort of like things that are kind of like very stand out, I guess. So we can kind of see that we have 3 times this, and then plus 1. So an example we'd say is that for our outermost function, g of x, we're taking 3 times something, and then adding 1. And what is that, something that we're adding? Or what we're plugging in for x is just that e to the 2x. So this is one example. If we were to take h of x and put it in with g of x, we would get 3e to the 2x plus 1. Okay. Another one that we can look for, and there's a couple of answers here. Oops. Okay, sorry about that. So there's a couple of answers that we can look for. Another one is we can see that we have this 2x right here, e to the 2x. So we could say that maybe g of x is 3e to the x plus 1. Well, what are we plugging in for x? We're just putting in a 2x. So in this case, we could do, if we plugged h of x into g of x, we get 3e to the 2x plus 1, which lines up with f of x. And another possible answer that you might see is g of x could equal x plus 1, because really we have this like 3e to the 2x, and we're adding 1 to it. And the thing that we're plugging in there is, there we go, h of x equals 3e to the 2x. So there's quite a few ways to approach these. You just kind of want to look for like parts of this that can be kind of broken apart. And a lot of times it's not too difficult just to go ahead and plug your answers back in to see if it actually lines up and works out. Okay, so going to part B of this, we're finding a composite function f of x equals 2 times x plus 1 to the 5th. So first we need to find two different sample solutions. So for our outer function, g of x, again, one thing you want to look for is kind of like parts or spots where you can kind of look where you can just like substitute something. So because we can see here this x plus 1 is all to the 5th power, it almost looks like we could just say this is 2x to the 5th, where we plug in x plus 1. So again, you kind of just look for like parts that can be pulled and then re-plugged in to get to your f of x. So a second example solution is you can think about it as we're taking 2 times something. Okay, so g of x could equal 2 times x, where that thing that we're plugging in is x plus 1 to the 5th. Okay, if you were to plug this back in, you get 2 times x plus 1 to the 5th power, which is f of x. So again, there's usually a couple different answers, and generally it's pretty easy just to go ahead and take h of x, plug it into g of x, and see if it lines up with f. Okay. So now moving on to number 30 here, we're given that f of g of x equals 3 times ln of 2x minus 1, and g of f of x equals ln of 6x minus 2. Find formulas for f and g. Okay, so one thing that we can look for here is kind of going back to that other one, is looking for sort of these parts that we can imagine substituting something in for. So one place that we could start is by looking at this 2 of x. So it almost looks like we could say this f of x and have it be 3 natural log of x minus 1. And then f of g of x is just where we plug in a 2x right there. So that would work for f of g of x, something kind of along those lines. Now we would just need to check g of f of x. So to do this, we're going to take f of x and put it in wherever we see x and g of x. So g of f of x, for our example here that we're testing, we just have 2 times f of x, or 3 natural log x minus 1. So this one here, we distribute our 2 out, and we get that g of f of x equals 6 natural log of x minus 2, which isn't quite what we were searching for. So we know that we need to try something different probably. So one thing that I can see here is that for g of f of x, it almost looks like we're taking the natural log and just plugging something in. So maybe what we can try is that g of x is just equal to the natural log of x, where all we're doing is plugging in this f of x at 6x minus 2 right there for x. So then what we'd have to do is check the other answer, f of g of x. So if we do that, we get So f of g of x, we're taking this ln x and we're plugging it in for f. So we're going to get 6 times the natural log of x minus 2. So that's also not quite what we were looking for. But we notice this is pretty similar to this here. The only thing it's missing is that there's a 2 on the inside here, and these are half. So maybe we can try one more thing, and we can go ahead and try maybe saying that f of x is 3 times this part here, minus 1. So if we try this one last time, let's try f of x equals 3x minus 1, and g of x equals the natural log of 2x. So we can see that if we do f of g of x, that lines up where we get 3 natural log of 2x minus 1, so that's right. And then for g of f of x, so we're plugging in f of x wherever we see g, we get natural log of 6x minus 2, which is what we were searching for. So that means that this here is our answer, 3x minus 1, and g of x equals natural log of 2x. So sometimes with these questions, it can be a little bit of trial and error, but generally you just kind of want to look for these parts that we can pull out and then plug back in, and then just test them, see if it works. Okay, so we're on to 31. For f of x equals 1 over x and g of x equals 1 over x plus 3, find the new function and its domain and use interval notation for each one. So let's start with A here. So we have f of g of x, or again, we can write f of g of x. So wherever we see x in f, we plug in g of x. So for part A, we have 1 over x, and wherever we see x, we plug in g of x. So we're going to plug in 1 over x plus 3. So because this is kind of like two separate fractions, this is going to work out just like that. Because this is like saying like you have 1 over 1/2, right? So if you multiply by 2 over 2, you would get 2 over 1, right? So that's kind of just if you have sort of like a weird fraction set up, kind of a way you can think about it. So for part A, our function f of g of x is equal to x plus 3. And the domain of this, well, there's nothing that's really going to give us a does not exist. So our domain is negative infinity to positive infinity. Okay. So now for part B, we're finding g of f of x. So for this one, B, we have 1 over x plus 3. And wherever we see x, we're going to plug in f. So we get 1 over x plus 3. So from here, we could try doing something similar to what we did on the last one and multiply by like an x over x. And that would get us x over 1 plus 3x. So this could be our function here. And so the domain of this is, well, we can't have zeros in the denominator. So we know that 1 plus 3 of x cannot equal 0. So solving this, we find that 3x cannot equal negative 1, x cannot equal negative 1/3. But there's one other thing here that we're missing, and that's looking right here at this. We multiplied by x over x. And whenever we do that, we're kind of taking away the possibility of x equaling 0. So if x equals 0, if we look back at our very first equation, we would have 1 over 0 plus 3. So whenever we did some rearranging, we found that we kind of got rid of that spot that x can't equal. So x also cannot equal 0 because whenever we first solved it, we had 1 over 0 if we plug that in. So our domain is going to be all numbers except for those two that we found. So in our function, we can go ahead and write it as x over 1 plus 3 of x, or 1 over x plus 3, but our domain is going to be negative infinity to negative 1/3, union negative 1/3 to 0, union 0 to infinity. Okay, and then for C, f of x plus g of x, we don't have to do anything fancy. It's just f of x plus g of x. So now we just need to find our domain. So again, we can't get 0 in our denominator, so x cannot equal 0. And we also get that x plus 3 cannot equal 0. So x cannot equal negative 3. So our domain is all real numbers except those two. So we can go ahead and write out. We go from negative infinity to 0, union 0 to the next number that we can't be. Oops, I made a mistake. Negative 3 is smaller than 0, so let's move that right there. So negative infinity to negative 3, union negative 3 to the next number, which is 0. And then we go from 0 all the way to infinity. So those are our answers right there.